So this is all joint work with Daniel, of course. And he gives really good talks. So this is true story. So he came in 2003 or 4. I was a grad student. He came to give a talk in the representation theory seminar. And it was a 2-hour talk in Eisenberg's seminar. And so there had a gap after 50 minutes. And I had some question that was stuck on my problem. So I asked him something. In that 5 minutes, he said something. He drew a picture, which I'll draw. And that basically became my thesis. And we are still sort of chewing on that. It's a little embarrassing, maybe. And that's the story. It's kind of a long story. And the question is still completely open, really. Well, we have results. But so in the beginning, I have a backstory, which is kind of a famous backstory. I'll give a little bit of that. And there'll be some big words, probably. But I don't care if you follow the details of this at all. I mean, this is just purely for motivation, because I'll spend like 50 minutes talking about one 13-dimensional complex ball quotient. So usually, I mean, this is a very receptive audience, I would think. This is about ball quotients. But usually, you have to sort of convince people to listen to that. So this backstory is to convince people to be interested. So it starts with the monster. The monster is a pretty big finite simple group. It's like order is about 8 times 10 to the 53. If you cannot hear me, please stop me. If I'm writing too small, please tell me. Something like this. And it's some crazy finite simple group. I mean, the size is impressive, but not that big. I mean, really. I mean, permutations in even permutations in 100 letters is a group of size 100 factorial over 2, which is, you don't think of that as a difficult group, because you have a representation on a faithful permutation representation on 100 letters. You give you 2 permutations of 100 letters, you can multiply them in 2 minutes. You just say 53 goes to 57, 57 goes to 39, and you just go 100 times. The difficulty with this object is not its size, it's that it has no small representation. So the smallest irrep is 19688 3-dimensional. So if you wanted matrices for these elements, it will be 196883 by 196883 matrices over F3. And from those, doing any calculation with this is still painful. But they figured this thing, they captured this guy in 1970s, which is a wonder. So if you wanted a permutation representation, again, it has to be like millions, I don't know the number, but millions of digits. So it doesn't act on anything small. It's just intrinsically this complicated object, and it's sort of a freak of nature, you might say. So if you're, I don't know, I mean, why should you care about it? It's a very valid question, I believe. So Conway and Professor John Mackay and Norton, they made these observations in the 70s, which made this guy famous, which linked this to some very classical objects, well-known objects from 100 years ago. The first observation was due to Professor John Mackay, who sadly passed away very recently. He noticed that this number he knew. So he would write these emails sometimes. He would say, you know, these 3 numbers also came out over there, like 3 numbers here and 3 numbers there. They had a knack for, crazy knack for observing these things. So this number is the Q coefficient of the J invariant of an elliptic curve. And then Conway and Norton calculated the next one and so on. So it turns out the next number is the sum of the next two irreducible representations of the monster, and the next one also is a small sum, and so on. And this came to know to be, so then they made a conjecture. The conjecture is the following. It's this famous Conway-Norton-Monshine conjecture. Monstrous Monshine. Now there are other kinds. There's a Matthew Monshine and so on. Monstrous Monshine. That these, if you take any So there should be a graded representation of the monster, that this monster should act on some, I'll call it V natural, the finite dimensional graded pieces, such that if you take the what is called the Mackay-Thompson series, take an element of the monster and you compute its graded trace. This trace of this element acting on the nth piece multiplied by q to the n. This generating series should be some sort of a modular function. That was the conjecture, and it seemed completely out there. This is a creature in finite group theory. This is, I don't know, number theory, what is going on. So this was proved in the 90s. A lot of people, and chiefly based on work of, this is a very famous story, I won't do this justice, Igor Frankl mainly, who showed that this thing is is a very interesting creature. This is a nice vertex operator algebra. So this has a lot of structure, which the monster preserves, and the monster is actually exactly the automorphism group of this thing. And then advisor Richard Borchard, he proved this conjecture in full with other people. So the statement is that, and he uses things from mathematical physics, so there's certain infinite dimensional Lie algebras involved with these, and that provides a link with this. You look at these infinite dimensional Lie algebras and take their twisted Weyl character formula, and those are known to be modular forms, and that's where this modularity comes from. So this is a theorem now, due to my advisor. Then this is what I'll call a normalized Hopf module for some genus 0 subgroup of SL2Z. What it means is that the corresponding to each element of the monster, so there's 193 conjugacy classes in the monster. For every element, there is some gamma in SL2Z, such that this is genus 0. So you take the upper half plane, mod gamma compactified is just a ball, is just P1. And this function is sort of the simplest uniformizer of this P1. It's the simplest function that you can now write on the upper half plane. That's what the word normalized is. That would identify it with this. That's the theorem. So that sort of made the monster famous, I believe. And the question that I want to address is, what is the natural space for the monster? Question is, what is the natural space for monster action? I mean, what is it an automorphism group of? And so far, the best answer, I think, is this V natural. This is some infinite dimensional object, and based on some computations in elliptic genera, people like Hirzebruch and Witten have, I won't say conjectured, has asked if there is a 24-dimensional real compact orientable spin manifold on which the monster acts in some nice way by diffeomorphism, such that if you take the associated action on appropriate cohomology groups, you recover some of these moonshine representations. Yes, please. What action? No, there is no complex geometry here. No, not at all. Yeah, but I definitely don't want to talk about what kind of structure this thing has. This is a completely different and deep story. So is there a 24-dimensional, what he calls monster manifold? So they have a precise statement. So there's this book by Hirzebruch, Berger, and Zhang called Manifolds and Modular Forms. It's book on characteristic classes, elliptic genus, and so on. There, this appears on page 87 as a prize question. And so he says, is there a 24-dimensional manifold with this invariant? The second Witten genus should vanish, the A1 genus should be this, and so on. And then he says, it would be marvelous to find a 24-dimensional manifold, as in the prize question, on which, in addition, the monster acts by diffeomorphism. Such an action would lift to an action on the tangent bundle and its exterior powers and so on, and then it would act on the cohomology of twisted Dirac operators. I have no idea what that means, but its indices are given by this twisted Reha genus. And if all this happens, then you'll have some key to construct lots of representations of the monster coming from geometry. Now, the big carrot that we have in this project that I'm going to tell you about is that we didn't start out looking for a 24-dimensional manifold. We were not looking in monstrous context at all. So we stumbled upon some object which seems to be around that dimension and have a monster action. So it's sort of at the end, we'll describe, this is a construction due to Daniel entirely, construction of a possibly orbifold, possibly manifold, on which it has the right dimension. There is a nice action of the monster, modulo certain conjecture that I'll describe. And the conjecture is a statement about the fundamental group of a ball quotient. So that's why this talk is here. So I'll talk about a 13-dimensional ball quotient whose pi1. So the object is to describe a 13D ball quotient whose pi1 seems monstrous. And I want to describe this object. So this will come to me as quotient of the 13 ball by some arithmetic complex reflection group. And that reflection group will come to me as reflection group of a complex lattice. So I have to describe for you the lattice, then the group, then what we know about this ball quotient. That's the plan. Questions so far? Yes?
I apologize if you've addressed this already, but where did the 24th dimension go? Is that something that came numerically?
Yeah. So all this, so the 24D is sort of, again, the best dimension because all sorts of exceptional things happen in 24 dimension. The chief reason for 24 is that there's this very, very exceptional object called the Leach lattice that exists in dimension 24. Which is the answer to all optimization questions in dimension 24, which got a Fields Medal day before yesterday by Marina Vyazovska, who basically proved that it's the answer to all optimization problem in dimension 24. It's the best sphere packing, it's the best energy optimizer, it's the best anything. Yeah. And there is nothing like it in other dimensions. So there's the E8, which is the baby cousin of this guy, and then there is the Leach lattice. And then if you ask me what is it in dimension 32 or 48, there is nothing like it. If you take the density of lattices, and there's Conway and Sloan's book has a graph, and E8 gets a nice peak, and Leach lattice gets a really big peak. And there, in other dimensions, there is nothing like it. Just that's how nature is. Yeah.
We're dreaming for big. Since we want this because it would be super.
No, it's because actually, I mean, and also the other reason, which is also equivalent reason, is that 24, you might say, is the first dimension where the curve, 12 is the first weight where the first cusp form arises, the discriminant form. So which is very related to this same statement, really, because the theta function of the Leach lattice is essentially that cusp form plus something. Yeah, afterwards, the connection with modular forms kind of break down because the dimensions of the modular forms become too big, so this uniqueness is kind of lost. So the 24 is sort of a sweet spot. Yes, so it doesn't match. So that's why. So there is some. Yes. So this is not the one. So there is some. So Daniel has a rather beautiful description starting from there to the 24 dimension. But that's absolutely valid. Yes. So this is not exactly the one, but we'll go from. This is advertisement. Okay. So now I can start in earnest. So the first job is to tell you about this reflection group, which is what I'll spend most of my time on. And a lot of it goes by analogy with Weyl groups. So I'll start there, and there's this analogy with reflection groups that keeps on repeating, so which is also another mystery, but maybe this is not the focus of this talk. So I'll give you a bunch of examples of reflection groups. The objective of the first few it is to drive home this analogy and also to set up my notation as we go along. Okay. So a bunch of examples of reflection groups. So one, let's just take the most classical thing, real spherical. And I'll take these Denkin diagrams. Let's just take the simply laced ones. I don't want to draw them. I guess these people know. Starting from this, you define a lattice called the root lattice, which is just a free Z module with basis vectors indexed by this diagram. And it has a Z lattice means it's a free Z module with a Z, that's an integral lattice. So it has a Z valued dot product. And the dot product is dictated by the graph. So to tell you how the inner product of these things go, it's 2 or minus 1 or 0, 2 if I equals j, minus 1 if you have an edge in the diagram, and 0 otherwise. That's the root lattice of the, so for corresponding to each of these, I learned about them in the representation theory class. There's a Lie algebra, and this is the root lattice of that Lie algebra. And then there is the Weyl group of that Lie algebra, which is the reflection group of this lattice. Let's call it ref delta. So this is the reflection group. It simply means all automorphisms of the underlying vector space, which preserves this dot product and preserves the lattice. Right? So that contains, it's very clean to describe this thing. This contains reflections in, so this is a finite reflection group. This is a positive definite dot product. A reflection in all shortest, which means norm 2 vectors. These are called roots. So we borrow that name from Lie theory. And the reflection group is generated by these reflections. Among them, I have these special roots that are indexed by the Denkin diagram. These are called the simple roots. And these dot products imply that whenever you don't have an edge, the corresponding reflections, simple reflections, commute because the roots are perpendicular, and when it's minus 1, then they braid in the usual manner. So it implies, so the dot products imply that this reflection group has a map from what I'll call Coxeter delta 2, which means, I'll explain, maps to deflection group. And this means, we write down what it means, Coxeter delta 2 is generated by some generators, C for Coxeter, and the relations are Ci square equals 1 if I equal for each I, Ci Cj Ci equals Cj Ci Cj if this, and Ci Cj equals Cj Ci if that. The 2 here is my notation, it just refers to this 2, that every element has order 2, because later we'll have complex reflections of order 3 when we'll have 3. And sometimes we'll have braid groups when we'll put infinite. Okay. And this is very well known that this is an isomorphism. The Weyl groups are these Coxeter groups. So this takes these Coxeter generators to reflections in these simple roots. This is as classical as a story gets. What am I forgetting? So that's the end of example 1, but I should do the only picture that I can draw, which is A2. A2 is this Denkin diagram. For that, there are 3 mirrors. These are the mirrors, and there are 6 roots. These are the roots. They're all root 2. Yeah, so I have defined the lattice for you, by the way, LA2. So these are the 6 norm 2 vectors of LA2. These 6. And among them, there is S1 and S2. And then the S3 is some of them, that's not a simple root. And these 2 are at 120 degrees. So you take one vertex for these 2, and you join them because they're at 120. Okay, so I want to say one thing, which again we'll repeat, is how you get the diagram from the, if I give you the group, how do you get this Denkin diagram? And I'm giving essentially the usual prescription, but in a funny way. So there is this special line here called the line of the Weyl vector. Let's call this rho. So I'll call it Weyl vector. And the simple mirrors, so which are the mirrors of the simple reflection. So that's here is S1, so here is S1 part. That's a mirror, right? This. So the reflection in S1 would flip like that. So here is the simple reflections mirror. So usually you say that you choose a Weyl chamber and you take the walls of the Weyl chamber. Those are the simple mirrors. I'm going to say that because in complex case I won't have chambers, you see. So I'm going to say that you take this Weyl line of this Weyl vector, and the simple mirrors are the ones that are closest to it in the spherical metric. The spherical metric here is just the angle. So I'm taking the mirrors which are closest to this line. And this actually gives you the Denkin diagram, not just simply list, all cases, all Weyl group. That's a statement. That's true. In the simply less case, this vector will be the Weyl vector. In the non-simply less case, it will be some other vector. But it's true. That's a slightly non-standard statement. I have not seen it elsewhere in print. Okay, so that's example 1. Example 2, I want to give just one real hyperbolic reflection group, which also has nice generators and relations, kind of like that. But maybe before moving on, I wanted to make an observation over there. So this thing that I said, I want to just record as an observation. Oops. For observation, that the simple mirrors are the mirrors closest to rho. So there exists a point rho in PV. V is this vector space where all this is happening. Such that the simple mirrors are the mirrors closest to rho. So that gives you the vertices of the Denkin diagram, and then the angles at which the mirrors meet gives you the edges. The angles at which the mirrors meet give edges of the diagram. Let's remember this. Yes, please. Yes, that is also true. For simply less case, that is obvious because the Weyl vector has height 1, but in the other case, you have to check kind of by hand. So, one real hyperbolic. But it's again the best one. And this one, I'm quoting my advisor, so it's not best. So I'll define, so it will be reflection group of lattice it has a name given by Conway, which is this. I'll write down what this means. Conway told me to call this even 25-1. So I'll call it even Mn. Even Mn, I can write down, it's an explicit thing, is an indefinite lattice. It's all tuples x1 through xm plus n in what I'll call Rm comma n. This means Rm plus n, but with the dot product which has m positive signs and n negative signs, x1 squared plus x2 squared plus xm squared, and then minus the rest. Such that either all the xi's are in Z, or all the xi's, when you add half, in Z. And so I doubled the integer lattice, then I have to half it to get something self-dual. You put the congruence condition. Now this, if m minus n is 0 mod, so there's a theorem, this is in, say, a course in arithmetic, that even self-dual Z lattices exist, indefinite. No, this is fine. Exist of signature m comma n. So this has signature m comma n. Exists if and only if m minus n is 0 mod 8. There's also a beautiful proof of this in Milner, Hauser-Muller. And in the indefinite case, it's unique. If m, n are both non-zero, then it's unique for every mn, and it's this one. Yeah. Say that again, please.
N plus n must be even, right?
Yes. The m minus n is 0 mod 8, so m minus n is 0 mod 2, so m plus n is 0 mod 2. Yes. It is even. So this is, some examples of this are II11, which I call a hyperbolic cell. So this is a signature 1-1. II80 is that Leach lattice up there, that E8 up there. That's the unique self-dual 8-dimensional. That is, I want to look at even 25-1. So, statement, this is how Conway used to like to state it, that this has a Denkin diagram, that the Leach lattice is the Denkin diagram of this reflection group. That was his sort of cryptic statement. It's saying that it has a Denkin diagram, it has a Coxeter representation whose vertices of the Denkin diagram is exactly the Leach lattice. And the edges are given by how far the points are in the Leach lattice. So there is a map from the Leach lattice. This is now the Denkin diagram to this gamma, and it's actually morphic. So the Leach lattice has appeared, and it's rather kind of in news, so I should tell you what it is. And that too, I can tell you the quickest definition I know is using this guy. So I've defined IIM even Mn, so I've defined even 25-1. So here is a definition of the Leach lattice, which I'll call lambda. To define lambda, you look at this vector. This is a vector in even 25-1. And this vector has norm 0. That is saying that 1 square plus 2 square plus 24 square is 70 square. It's actually the only solution to this equation. This equation, 1 square plus 2 square plus m square equal to n square. It amounts to some elliptic curve counting integral points on some elliptic curve and doesn't have much. So this vector has norm 0 in even 25-1. So if you take its perp, this has appeared in some talks here. It is singular and it contains the guy. So you quotient it out. Now it's a positive definite thing. That's the Leach lattice. It has all sorts of other definitions. So there are hundreds of definitions in Conway and Sloan, but this is the quickest. But this is also kind of, you cannot work with this definition, but well, it's honest to God definition. So then, what is this statement? This statement hides some very beautiful real hyperbolic geometry. And the proof of this is a 3-page paper by Conway and Slow, and it's called the Unique Even Unimodular Lattice in Hyperbolic 25 Space or something. And it's many of our calculations are actually children of this calculation. So that's why I wanted to mention this actually. So there's some very beautiful real hyperbolic geometry associated to this, which I want to just draw. I won't write much. So this lattice also has even 25(1) has reflection in all norm 2 vectors, which are the roots, again, just like before. Among them, there are these things called Leach Roots. So to draw, so this thing acts on H25, right? It's a signature 25(1) thing, so it acts on real H25. And there is this point sitting in the boundary. This non-zero vector. And it's a very strange looking cusp for this reflection group in that there is no mirror that goes through here. That corresponds to the fact that Leach lattice, even being a even self-dual lattice, has no norm 2 vector. The norm 2 vectors, orthogonal complements, are the mirrors, and there is no mirror going through here. So you can draw a horoball of radius 1, and then that's the first time some mirrors touching it. Maybe it's like this. And it's overly simple. It's a cartoon, of course. And then as you come here, there are infinitely many walls going, but there is no mirror actually going through this point. That's what it looks like. And there is an explicit description of what these mirrors are. So what you can do is you can write this guy as the Leach plus this choice of this row, split out this lambda, and then you can break the Lorentzian lattice like this. And then you have a vector here, you can write it as V, M, N. So but these are integers, and this is a Leach lattice vector. So in particular, for every Leach vector, I have a root, which I'll call a Leach root, which goes lambda, which is 24 coordinates, and then 1, and then you can fill in the last coordinate with the condition that its square has to be 2. So these are called the Leach roots. These are our simple roots. And these are exactly these walls. One for each Leach vector. So there are infinitely many walls, but the angles at which they intersect is governed by their distance in the Leach lattice. And then the relations that this hyperbolic reflection group has, the Coxeter relations, are exactly governed by this lattice. And then if you want to prove that these reflections actually generate this reflection group, you do it by height reduction, like you would do over there as well. If you want to prove that the simple reflections generate the reflection group, you take some random mirror and you try to reflect it in the simple reflections to try to bring it closer to the Weyl vector. And it always works, and that's how you prove that the simple reflections generate. You do the same thing here. You take some other mirror and you try to reflect it in these to bring it closer to this Weyl vector, which is at the boundary. So you decrease the horocyclic distance. And this essentially is Winberg's algorithm in this case. It's a translation of Winberg's algorithm. Yes? Say that again, please. Yes? No, I would even think there are bigger. Yeah, there are all these finite Weyl groups that would be sitting in there. So, yeah. Yeah. But I want you to sort of remember this picture, because this will again come back. Okay. So, example 3. So, by the way, I want to repeat that this observation again holds. I have this special point. This time you have to stretch your imagination a little bit. It's not in the space, but it's in the boundary, but whatever. And these are exactly horocyclic distance 1. And everything else is strictly further away. And you take this special point, and the closest reflections generate, and makes the Denkin diagram. Not too bad. Example 3, finite, so complex spherical reflection groups. And again, I'll start with some Denkin diagrams, very few this time. Okay? And for these Denkin diagrams, I'll make some lattice, but these are going to be complex lattices, and all my arithmetic for the last 20 minutes is going to happen over this ring of Eisenstein's integer, which is z adjoint cube root of unity. Omega is to 2 pi I over 3. So whenever you see z, you have to replace it by that. So here is a picture of the number ring. Here is 1, here is omega, and I want to name this vector, which is square root of minus 3. I'll call it theta. Okay? Those will play a role in the arithmetic. So you start with these Denkin diagrams, and you make some lattice, I call L delta E. Replace Z by E. And here, to make the arithmetic work, you have to do 3 theta and 0. Okay? That's what makes the arithmetic work. Then I want to look at the reflection group of these things. These are Shepard-Todd groups. These are 4 of the exceptional Shepard-Todd groups. And it contains reflection in all norm 3 vectors. Oh, this picture doesn't need to be here anymore. And then these dot products imply that the corresponding complex, so this contains reflection, I should say, order 3 complex reflection. Omega reflections. And these things have been defined in this seminar. So usually I have to define these things, but now I don't. It's a happy thing. In the shortest norm 3 vectors, which are called roots, and those dot products imply that you have a map from Cox delta 3 to this. Now the only difference is that these things are order 3. And again, these are isomorphisms. This is all well known. I think goes back to Coxeter. I just want to remark that this observation still holds, which is probably not that well known. So here the space in question. So for example, if you take the biggest one, A4, this one is actually again E8. See, it's 4-dimensional over E, so it's 8-dimensional. So it's the complex version of E8. And for this one, for example, you have 40 mirrors. Out of that, I'm choosing 4 of them and calling them simple mirrors. Again, I'll call them simple mirrors. And so this thing is acting, so the reflection group of this is some finite subgroup of U4. You're acting on CP3. And there is a unique point in CP3, or orbit of a point, such that these 4 are exactly the closest, and you reflect in them and they generate. So that observation still holds. So that sets up all my notation. Now I can do example 4, which is the real one, which is the complex one. This is the complex hyperbolic one that this story is about. But we have set up all our notation now, so this should go quite quickly. And in fact, the complex hyperbolic one is the complex cousin of this. Is the complex analog of this one. Exactly. So for some reason, I started looking at it, and it seems to have some monstrous connection. So let me now have to tell that story. Complex. And every time I'm starting with a Denkin diagram, so here too, I will start with a Denkin diagram. And I'm skipping a little here. The Denkin diagram, I'll just throw this at you, is going to be, I'll call it D this time, that's what I'm used to. is the incidence graph of the projective plane over F3. So the projective plane over F3 has 13 points and 13 lines. So this is a graph with 26 vertices, one for every point, one for every line, and you join two things. If this is a point, this is a line, and the point is on the line. Okay, so that's the graph. Here is a picture of that graph. So the incidence graph, the 13 points here, 13 lines here. It's easy to remember. You take 3. 3 square is 9. 9 times 3 is 27, which is 1, and you throw in 0. Okay, so it's mod 13. So 3, 9, and then 1, and then 0, and then you move and shift cyclically. That's this picture. So that's the incidence graph of P2F3, and it's a nice symmetric graph. That's going to be my Denkin diagram. Okay? And I'm going to do exactly that construction that is up there still. So I'm going to take L. Well, it's not quite going to be it, because you'll say immediately this is 26 dimensional. 26 vertices. Well, but this is also singular. It has a 12-dimensional radical. So then this happens to be singular, and which means that it has a 12-dimensional subspace, the vectors of which are perpendicular to everything. So to kill that part to get something non-degenerate, if you kill the radical, that's my L. That's the complex, that's a 14-dimensional, so the signature 13, 1. That's one definition of it. But for now, that definition will do, because that definition immediately gives you 26 norm 3 vectors which are at whose dot product is governed by that diagram, just like we say. Yeah, so that those dot products I told you imply that Cox, now I have to save this diagram. Let's draw it here. That the Coxeter group of D with 3's map to the reflection group of L. This is now a complex hyperbolic reflection group acting on the 13 ball. Yeah. Just from this definition, if you believe. This is just checking some calculation. But I can make it actually even more concrete. You could just take E13-1, so 13 positive with the standard dot product. And then I can tell you what 26 vectors to take. You see, I wrote pluses. I need 14 coordinates for E13-1. So these are 13 coordinates. And let's add another coordinate and put minus signs there. So now these are 13 norm 3 vectors. You see, 4 pluses, 1 minus. Makes, but, or you can even put plus, I believe. Okay, that's fine. Maybe minus, I don't know, something like this. But the norm is this square plus this square plus this square plus this square minus that square. So it's norm 3. So these are 13 norm 3 vectors. Let's call them L1, L2, L13. And then P1, P2, P13 are going to be just 0, theta, 0, 0, 0, 0, 0, theta, 0, 0, 0, up to 0, theta being square root of minus 3. So if you take those 26, I sort of built it out of that diagram. They have dot products governed by that diagram, of course. So it has that dot product, so that tells you that you have this map. Theorem 1, this map is onto. So this reflection, this hyperbolic reflection group is generated by these 26 order 3 reflections, which obey those Coxeter relations of that graph. Okay, so now why this got us excited? Because something else was known. If you take that same graph, the very reason we looked at this graph is because if you take 2's here, then that maps onto the bi-monster. So it's just M cross M with a Z mod 2 acting by switching the 2 copies, and you take the semidirect product. This thing is called the bi-monster. And this is theorem of a bunch of people, Conway, Norton, Ivanov. Ivanov is probably who did the most hardest part. It's like 2 books of him classifying some finite geometries, and I don't understand this at all. Yeah, so there's no direct map. What's going on? Of course, Cox d infinity maps to both, you could say that. That just means you forget that the generators have order 2, but this is a group which I know nothing about. This is some non-finite type Coxeter diagram. Well, what can you say about this? So the objective is to get some sort of relation. I mean, you see, this is a very easy group to understand in some sense. It's an infinite group, but these are 14 by 14 matrices on my computer. This is just acting on 14-dimensional vector space with a Hermitian form, with entries in E. This thing I know is not going to have any small representation, for sure. So some connection has to go in some roundabout way. So to say that, I'm going to tell you a little bit in 5 minutes how this thing is proved. And again, it requires some complex hyperbolic geometry in the spirit of what I just erased here, Conway's argument. 10 minutes, that should be plenty. So the proof of this theorem goes, I'll say 3 things, basically 3 lines. One, copy Conway working at a Leach roots, because there's a definition 2 of this thing. It's also the complex Leach lattice plus a hyperbolic cell. And so there is a so here is now the 13 ball on which this reflection group is acting. And there is, if you split it like this, it fixes this, I'll call it rho lambda. It's the vector that goes 0, 0, 1 in this coordinate system. Yeah, and then exactly like Conway, by doing some height reduction, you can prove that there are these infinitely many Leach mirrors that go touching this horoball, those are the closest, that they generate. And that's a height reduction argument. Almost work, doesn't quite work as nicely, but it almost does. And this argument works precisely because this Leach lattice is so dense. It is proved to be the densest packing by far. If the Leach lattice was epsilon less dense for any positive epsilon, then this argument will break down. So the Leach lattice is exactly optimal to make this argument work. So you get infinitely many generators this way. Then, so that's 1. 2 is, this is a trick that Daniel invented. There's some Heisenberg group sitting in this reflection, some discrete Heisenberg group sitting in this reflection group, acting as, so it's all automorphisms of this which stabilize this point and act trivially on this. That's a copy of the discrete Heisenberg group. Using that action of that, you can reduce from these infinitely many generators, I could reduce it to 50 generators. And then I have to get our 26 generators. And there is some nice geometry associated to our 26 generators as well. These 26. These 26. You know, Ci going to this. And here is the geometry. You see, this D I keep saying is like the Denkin diagram, and it has a lot of symmetry. Because it's the incidence graph of P2F3, PGL3F3 acts on it. In fact, there is extra Z mod 2 that also acts on it by flipping the points and the lines. So these are my diagram automorphisms of my Denkin diagram. So this acts on the diagram, so it acts on the lattice, because I made the lattice out of the diagram just like you build root lattice. It acts on the lattice, so it acts on the underlying hyperbolic space. After all, what is this hyperbolic space? It's just, you could take it to be negative norm lines in the underlying vector space. So it acts on the ball, and there is a unique fixed point. We'll call rho. And then these 26 mirrors of these 26 mirrors are exactly the ones that are closest. So there are 13 corresponding to the 13 points. There are 13 corresponding to the 13 lines. These 13 are orthogonal because there is no edge between 2-point mirrors, you see, because they are all orthogonal. I have edge only when something is a point and something is a line. So these 13 are orthogonal, they meet at a point. So these are, we'll call them P1 perp, P13 perp. These are L1 perp, L13 perp. I've written Pi and Li for you explicitly in coordinates there. And PGL3F3 fixes this point, so it fixes this CH1. And this rho is the midpoint of the real geodesic joining those two. And then the theorem is that let's call them S1 perp through S26 perp. S1 perp through S26 perp are closest to rho bar. And the reflections in them generate. So now what I do is after I have found 50 reflections near this list cusp, I do a height reduction with respect to this point and try to move them to these. And it kind of works. So that's the proof of this theorem. Now get back to this question, what is going on? So the idea is to replace this by something geometric. And after you see all this, you would immediately say, well, it's the pi1 of the ball quotient. So that's like the braid space. So you look at pi1 of x, where x is the ball minus the mirrors mod gamma. So you take this ball quotient. In that ball quotient, I have loops corresponding to every mirror. So if you give me one of these mirrors, I can go up to it. So I take the base point here, rotate 120 degree, and then go to the reflected point. And that, in the quotient, gives me a loop. Let's call that GI. So I have G1 through G26. And first thing we proved is that there is a map, meaning those GIs obey the braid and commute relations. And then the main theorem that is like a 100-page calculation of 2 papers with Daniel is the second arrow. So this is on to. So this is theorem. This is some crazy computation. And every step you have to sort of pray to the Leach lattice. Because it's so special, it has all sorts of special properties, and something saves you at every step. But you see, I mean, it cannot. So it's literally making explicit homotopies. In 13-dimensional, and these mirrors are punctured by, there are infinitely many mirrors puncturing this space and controlling when some path, you're trying to move some path, if there is some mirror puncturing through, it's just impossible in general. So you have to use all sorts of things, and I don't want to go, but in particular, this argument that I gave here, that's a start. You kind of try to do that. And then you sort of bootstrap your way up from there. So there's this fundamental group that, by definition, essentially, it's an orbifold fundamental group, of course. So it's, even after you remove the mirrors, there are stabilizers. Like this point is not on any mirror, I know it. And it has a big stabilizer. Yeah, but that's fine. You get a map from here when you impose the relation that these loops have order 3. The Monstrous Proposal conjecture is that when you impose the condition GY square equals 1, then you should get the bi-monster. So this is Allcock's Monstrous Proposal. This goes back to around 95-ish, I think. When, I don't know how he made it, because none of this, almost nothing of what I have told you was known at that point. It was very bold at that point, but now we have lots of evidence. There's some extra relation here that you need to satisfy to get the reflection group in the monster, which is called the deflection relation. And it's like the biggest cycle in that graph is a 12 gone. It's a clock. And it comes from that. So because this clock sits in this Denkin diagram is infinite. It's a fine diagram. So this defines the Weyl group of type that A11 semidirect or Z11. So to get a finite group, you at least have to kill this free abelian part. And if you do that for every 12 gone that sits in this D, that's what Conway called deflation, then you get the bi-monster. Exactly. So we checked that the deflation holds here. And I would say, we are reasonably confident. Daniel was going to send me an email, but he didn't. He's checking something right now, and that it holds here as well. If that is so, can I just try to explain where the conjecture stands now and how it yields a 24-dimensional object. So that would take another 3-4 minutes. I don't know if I have any time left. I have 2 more minutes. Maybe I'll take 2 extra. So let's assume that this deflation holds here as well, which is a little leap of faith at this point. But if you knew that, then you would know that this quotient, the conjecture is saying that this fundamental group of the ball mod the normal subgroup generated by the square of these meridians, these explicit 26 meridians, is the bi-monster. Let's call it bi-monster. If you believe that the deflection holds here, and there is reason to believe this because this is actually a relation in a 9 sub-ball that sits in this. That's a separate story that I didn't get to, and that 9 sub-ball is the biggest Deligne-Mosto example, which is the moduli space of 12 points on P1, and there you can prove that this deflection relation holds, and then you can lift that argument, we believe. Yeah, so it comes from that connection. Maybe we would love to ask you more about that. Daniel definitely would have. So if you believe that this relation holds here, then this quotient satisfies all the relations of the bi-monster. Because it already satisfied all the Coxeter relations, and now you force the square to be 1. Deflation also holds. So it's actually a quotient of the bi-monster. Yeah, I mean, but then the monster is a simple group. The bi-monster doesn't have very many quotients. It has the trivial group or Z mod 2 or the bi-monster. So this quotient, current status, has 3 possible orders, 1 or 2 or 10 to the 103-ish. 1 can be ruled out because there is some parity kind of argument. There is this Borcher's automorphic form with singularities, zeros exactly along the mirrors that you can construct on this complex 13 ball using this singular theta lift machinery, which Daniel did at some point. Using that, you can rule out 1. So it's 50-50. Order 2 or order 10 to the 103. So which I have no idea. I mean, it will be a cruel joke for me if it was this. But other than that, I don't think the universe cares about me. So it could be. I don't know. That's the status. The last thought, what you asked in the beginning. So this ball quotient, the conjecture is saying that the bi-monster is a quotient of the pi1, which means that there is some ramified covering where the deck group is the bi-monster. Take the universal cover and then quotient out by whatever relation you need. Yeah, so there is some covering of this on which the bi-monster acts. To get this thing, you remove those hyperplanes. You remove this family of hyperplanes. So you can fill in over that. So this thing is sitting in the ball mod gamma, which is X disjoint union this extra mirror divisor. I'll call it, I don't know, mirror mod gamma. And this is arithmetic group, but I forgot to say that the reflection group is the whole automorphism group in this case. Just the fact that it is finite index is remarkable. That was essentially the first paper of Daniel on this, that this is finite index in its automorphism group. And if you want, so that means that it's arithmetic. If you want arithmetic complex hyperbolic reflection groups, in high dimensions, very few are known. I mean, so dimension 9, the Denkin-Mosto example was the biggest one, and this is still the record holder, this dimension 13 one. So anyway, so this is sitting in here. So it's that the open part plus the exceptional divisor. So the gamma is transitive on the mirror. So this is a reducible divisor here. And you'll hope that there is machinery for filling in over that if you have this cover. This cover is conjectural based on the Monstrous Proposal. But if you have this covering, then you could fill up over this. This I'm told by complex geometers. Kyoji Saito told me that there are general machinery of Stein spaces which allows you to fill in over these things. I have no idea, but I'm just quoting people. So you'll get something here, X tilde union some extra stuff, so some exceptional divisor that sits on this mirror. And here, the deck group you can show This you can show now is exactly the monster. And this is sitting over the mirror. So this is complex 12-dimensional. So this is real 24-dimensional. And if this part works, then it's apparently automatic that this is smooth. That also, I'm just quoting people, what people have told me. Yeah, so this now is a candidate object, which is 24-dimensional, on which the monster acts by deck transform. Last thought, these proofs are horrible, and we'd like to make them useless. I mean, so in this 9-ball, the arguments are so nice because it's a nice moduli space. You can show these Coxeter relations hold trivial because it's 12 points on P1, points interchange, so of course the Coxeter relations hold. So everyone I talk to tells me, and Daniel, I don't know, Dolgachev, Luenga, what is this a moduli space of? I don't know. It would be lovely to know that. Yeah. Thank you.